derived for colligative properties hold good only for solutions of non-electrolytes, as there is no change in the molecular state of the solute. When a solute undergoes dissociation or association in a solution, then the number of particles of the solute in the solution increases or decreases respectively. Thus, the colligative property changes accordingly and we get abnormal results. Inorganic acids, bases, and salts undergo dissociation either completely or to some extent in an aqueous solution. For example, if 1 mole of potassium chloride, KCl, is dissolved in water, then the aqueous solution contains 1 mole of potassium ions and 1 mole of chloride ions. In such cases, the number of effective particles in the solution increases, and therefore, the observed colligative properties like osmotic pressure, elevation of boiling point, and depression of freezing point are much higher than those calculated on the basis of undissociated single molecules. Further, as molar mass is inversely proportional to the colligative property, the experimentally determined molar mass will always be lower than the true value for dissociation. For KCl, as the number of particles becomes double, the observed colligative property is double than the expected value, while the observed molar mass is half the expected value. That is, 74.5 grams divided by 2, which is equal to 37.25 grams. Similarly, there are many organic solutes that undergo association in a non-aqueous solution. That is, 2 or more molecules of the solute associate to form a bigger molecule. For example, ethanoic acid in benzene exists as a dimer due to hydrogen bonding. Thus, the number of effective molecules or particles in the solution decreases. If the association of ethanoic acid is assumed to be complete, then the observed value of the colligative property will be half, and the molecular mass would be double the expected value. When the molecular mass of a substance, as determined by studying any of the colligative properties, comes out to be different than the theoretically expected value, the substance is said to show abnormal molecular mass. In order to account for all such abnormalities, Dutch chemist J.H. vanthoff, in the year 1880, introduced a factor, I, known as vanthoff's factor, which represents the extent of association or dissociation of a solute. Quantitatively, vanthoff's factor I is defined as the ratio of the observed colligative property to the calculated colligative property. Thus, the expression for I can be written as I equal to the observed colligative property divided by the calculated colligative property. Now, since colligative property is inversely proportional to molar mass, I, in terms of molar mass, becomes I is equal to normal or calculated molar mass MC divided by abnormal or observed molar mass MO. Further, as the colligative property depends directly on the number of particles present in a solution, It can also be written as I is equal to total number of moles of particles after association or dissociation divided by number of moles of particles before association or dissociation. Note here that the calculated colligative property takes into account the assumption that the non-volatile solute has undergone neither association nor dissociation. The value of vanthoff's factor is less than 1 if there is association of the solute in a solution, and is greater than 1 if there is dissociation of the solute in a solution. All substances that undergo neither dissociation nor association in a solution, I is always unity. If a solute undergoes 100% dissociation, then vanthoff's factor is equal to the number of ions produced from one molecule of the solute. For example, the value of I is 2 for aqueous KCl. This signifies that KCl has dissociated completely into potassium and chloride ions. The value of I equal to nearly 0.5 for ethanoic acid in benzene, which signifies that nearly the entire ethanoic acid has undergone association and exists as a dimer. The modified equations for colligative properties using the vanthoff's factor can therefore be written as relative lowering of the vapor pressure of solvent P1 naught minus P1 divided by P1 naught is equal to I multiplied by N2 divided by N1. Elevation of boiling point delta Tb is equal to I multiplied by Kb multiplied by M. Depression of freezing point delta Tf is equal to I multiplied by Kf multiplied by M. Lastly, the osmotic pressure of a solution pi is equal to I multiplied by N2 multiplied by R multiplied by T divided by V. The degree of association as well as the degree of dissociation are represented by the letter alpha. Let us now derive a relation between vanthoff's factor I and the degree of association alpha. The degree of association of a substance, alpha, is defined as the fraction of the total substance that exists in the form of associated molecules. That is, the number of moles associated divided by the total number of moles taken. Consider 1 mole of solute A dissolved in a given amount of solvent. And suppose that n molecules of A associate to form associated molecule AN, and an equilibrium gets established between Na and associated molecule AN. If alpha is the degree of association of the solute, then at equilibrium, 1 minus alpha moles of A are left in unassociated form, while alpha divided by n moles of AN are present in associated form. Therefore, the total number of moles of particles after association is equal to 1 minus alpha plus alpha divided by n. If there is no association, then the number of particles is equal to 1. Substituting the values of the number of particles in the relation I is equal to total number of moles of particles after association or dissociation divided by the number of moles of particle before association or dissociation. We get I is equal to 1 minus alpha plus alpha divided by n divided by 1. On simplifying for alpha, we get alpha is equal to 1 minus I multiplied by n minus 1. Thus, if the value of n and vanthoff factor I is known, then the degree of association alpha can be calculated. On the same lines, let us now derive a relation between vanthoff's factor I and degree of dissociation alpha. The degree of dissociation of a substance alpha is defined as the fraction of the total substance that undergoes dissociation. That is, alpha is equal to the number of moles dissociated divided by the total number of moles taken. Suppose one molecule of electrolyte A gives n number of ions on complete dissociation. That is, in general, A dissociates to give n1 moles of B plus n2 moles of C plus and so on, such that n1 plus n2 plus and so on is equal to n. If we start with 1 mole of the solute, at equilibrium, we have 1 minus alpha moles of the undissociated molecules and n alpha moles of the ions. Thus, the total number of particles present at equilibrium is equal to 1 minus alpha plus n alpha, or 1 plus n minus 1 alpha. Substituting the values of the number of particles in the relation, I is equal to total number of moles of particles after association or dissociation divided by number of moles of particles before association or dissociation. We get I is equal to 1 plus n minus 1 alpha divided by 1. On rearranging, we get alpha is equal to I minus 1 divided by n minus 1. Knowing the value of I from the colligative property measurements, the degree of dissociation alpha can be calculated. Let us now solve a numerical problem based on the association property of a solute. Acetic acid CH3COOH associates in benzene to form a dimer. 1.65 grams of acetic acid, when dissolved in 100 grams of benzene, elevates the boiling point of benzene by 0.36 Kelvin. Calculate vanthoff's factor and also the degree of association of acetic acid. Kb for benzene is 2.57 Kelvin kilogram per mole. The first step is to list the given variables. W2 is equal to 1.65 grams. W1 is equal to 100 grams. Delta Tb is equal to 0.36 Kelvin. Kb for benzene is 2.57 Kelvin kilogram per mole. Molar mass of acetic acid M2 is equal to 60 grams. Vanthoff's factor I and degree of association needs to be calculated. Let us first calculate Vanthoff's factor I. Substitute these values in the modified equation for elevation in boiling point. Elevation of boiling point delta Tb is equal to I multiplied by Kb multiplied by W2 multiplied by 1000 divided by M2 multiplied by W1. On solving for I, we get Vanthoff's factor I is equal to 0.5093. Substituting for I in the equation, degree of association alpha is equal to 1 minus I multiplied by n minus 1. Now, n for acetic acid is 2 as it exists as a dimer. On solving, we get degree of association alpha is equal to 0.98. Let us now solve a numerical problem based on the dissociation property of the solute. A solution containing 1.23 grams of calcium nitrate in 10 grams of water boils at 100.97 degrees centigrade. Calculate the degree of dissociation of the salt. Kb for water is 0.52 Kelvin kilogram per mole. The first step is to list the given variables. W2 is equal to 1.23 grams. W1 is equal to 10 grams. Delta Tb is equal to 100.97 degrees centigrade minus 100 degrees centigrade, which is equal to 0.97 degrees centigrade. Kb for water is 0.52 Kelvin kilogram per mole. Molar mass of calcium nitrate, M2, is equal to 164 grams. The degree of dissociation needs to be calculated. For finding the degree of dissociation of the salt, we first need to calculate vanthoff's factor, I. Substitute these values in the modified equation for elevation and boiling point. Elevation of boiling point delta Tb is equal to I multiplied by Kb multiplied by W2 multiplied by 1000 divided by M2 multiplied by W1. On solving for I, we get vanthoff's factor, I, is equal to 2.48. Substituting for I in the equation, degree of dissociation alpha is equal to I minus 1 divided by N minus 1. Now, N for calcium nitrate is 3. On solving, we get the degree of dissociation. Alpha is equal to 0.74.